Hey guys, welcome to this news story. Before we go anywhere, take a moment to get comfortable. Let your body settle into the place you've chosen for the night. Adjust your pillow if you need to. Let your shoulders soften and allow the day to loosen its grip. There's nothing you need to focus on right now, nothing you need to remember. For the next 2 hours, you won't be asked to think, react, or decide anything at all. In this story, you'll be gently carried on a slow, uninterrupted flight around the largest star ever discovered, a giant so wide that it would swallow the orbit of Jupiter if placed in our solar system. There will be no sudden turns, no sharp changes, just a smooth, steady path around its enormous surface, meant to help your breathing become slow, and even as you listen, with your eyes closed. I'll be here at the beginning to guide you in, and then, little by little, my voice will soften as you fall asleep while this massive star continues to burn in your imagination. As we begin, imagine yourself weightless, supported, safe, and unhurried. Below you stretches a deep red surface of rolling fire, rising and falling in waves larger than entire solar systems. Light pours outward in every direction, steady and constant, from a star nearing the end of its long life. We'll circle it together, slowly, at a pace meant for rest. For now, just let yourself lie still and allow the journey to begin. From a distance, the star appears as a point of light, bright against the dark canvas of space. As you move closer, its light grows steadily stronger, filling the visual field with a soft, white glow tinged with pale yellow and hints of orange. This is not light in the sense we experience on Earth, filtered through atmosphere or softened by clouds. It is pure radiation, traveling across vast distances uninterrupted. You notice that the light is not uniform. There are subtle fluctuations, tiny changes in intensity that reflect the turbulent processes occurring on the star's surface. Even from millions of kilometers away, these patterns are perceptible, though only faintly. Each pulse and shimmer is a sign of motion, energy, and the constant churning that defines the star's behavior. As you draw nearer, the scale becomes apparent. This is a star far larger than our Sun, several times wider in diameter. Its immense size is difficult to comprehend at first glance. From this vantage point, the star is no longer a simple point of light, but a sphere of color and texture, slowly rotating. You can see hints of the granulated surface, the pattern of convection cells that move energy from the interior to the outer layers. These granules are not individual objects, but regions where hot plasma rises and cooler plasma sinks, creating a subtle, shifting mosaic. Their edges glow more brightly than the centers, revealing temperature differences that can reach several thousand degrees. The rotation of the star is gentle but perceptible. Unlike a solid body, the star rotates differentially. The equatorial regions turn slightly faster than the poles. From this distance, the effect is mostly in the slow movement of surface patterns, in the gentle drift of bright regions across the face of the star. You can track a single granule for several minutes before it changes or merges with its neighbors, evidence of the constant turnover of material. These motions are powered by the star's immense internal energy, produced in its core through nuclear fusion. Even here, far above the core, the effects are visible. The color of the star is an important cue to its temperature and age. It is pale yellow with subtle orange highlights. This indicates a cooler surface than a blue star, but hotter than a red giant of similar size. Spectroscopy, if applied, would show the presence of hydrogen, helium, and trace heavier elements in the outer layers. These elements are responsible for absorbing and emitting light at specific wavelengths, giving the star its precise hue. Each photon reaching your eyes carries information about these elements, about the pressure and temperature of the gas, and about the motion of material across the surface. Moving closer, the star's limb darkening becomes more apparent. The edges of the star appear slightly dimmer than the center. This is a natural effect of looking through layers of gas at different temperatures and densities. Near the center, you are seeing deeper, hotter layers, while at the edge, your view passes through more of the cooler outer layers. This subtle shading is not uniform, however. Localized bright regions may appear along the limb, caused by active areas or convection currents. Each variation is small but measurable, adding depth and structure to what at first seemed a simple glowing sphere. The scale of the star also influences its gravity. From this distance, the pull is not strong enough to be felt directly, but its effects on nearby objects are clear. Any orbiting material, such as dust, gas, or potential planets, moves in precise paths determined by the star's mass. The orbits are stable over long periods, though they may be influenced by the star's rotation or by interactions with other stars in the same region. Observing the motion of these objects provides another measure of the star's size and gravitational pull. As you continue your approach, the light intensity increases. Noticeably, though in space, there's no atmosphere to scatter it. This light is harsh in a direct sense, yet from a distance it can be observed safely with appropriate shielding or sensors. The surface of the star is far too hot to touch, radiating millions of watts per square meter. Even without direct contact, the energy is detectable, and instruments could measure its spectrum, fluctuations, and polarization. Each measurement gives insight into the processes occurring within the star, from the slow rotation of its outer layers to the rapid rise and fall of hot plasma in convection cells. The star is surrounded by a faint halo of material. This is the outer atmosphere beginning to rise from the photosphere into the chromosphere and corona. At this distance, the halo is subtle, mostly visible in ultraviolet and X-ray wavelengths. It marks the transition between the visible surface and the more tenuous, extended outer layers. You can see wisps and structures within this halo, shaped by the star's magnetic field and by the motion of charged particles. Over time, these features shift and change, responding to magnetic activity and the continuous movement of plasma from the surface. As you complete this first arc of approach, the star's enormity becomes almost tangible. Its diameter is measured in billions of meters, hundreds of times larger than our Sun. To orbit this star at a distance comparable to Mercury's orbit around the Sun would require crossing a space of unimaginable scale. The curvature of the surface is gradual, almost imperceptible from this distance, yet each step closer reveals more detail. The texture of the photosphere, the rise and fall of granules, the subtle differences in brightness, all these become easier to perceive as your relative distance decreases. The motion of the star itself is also noticeable. Though stars often appear fixed against the night sky, this star moves relative to its neighbors. Its velocity through the galaxy is slow on human scales, but over months or years, the motion becomes measurable. Approaching from this perspective allows you to see the direction of travel, any wobble due to companions, and the slight parallax that gives clues to its distance from Earth. This motion, combined with rotation and surface dynamics, creates a continuously changing view, never static, never fixed. From a sensory perspective, even in simulation or observation, the light from the star has texture, not texture in the sense of touch, but in the shifting brightness, the way edges blend into softer regions, the subtle patterns of activity that move across the surface. These cues give the viewer a sense of depth, of three-dimensionality, and of energy and motion. They prepare the observer for a closer approach, for observing more complex layers and processes in the next stages of the journey. The immediate environment around the star is filled with radiation, mostly in the form of photons and particles. Solar wind begins here, a continuous outflow of charged particles carried by the magnetic field. At this distance, the wind is sparse, but its direction and speed can be measured. Structures within the wind, show the influence of magnetic loops and coronal activity. Observing these patterns provides insight into the star's activity cycles and the forces shaping its outer atmosphere. As you continue to circle the star at this distance, your perspective shifts slowly. Observing from different angles reveals subtle asymmetries. The rotation causes a slight flattening at the poles. Active regions on the surface become more or less visible depending on your viewing angle. Sunspot like features appear as darker patches, slightly cooler than the surrounding areas, hinting at magnetic phenomena below the surface. These regions are scattered unevenly, giving the star a dynamic, living appearance. The light reaching you changes subtly as well. While the star is mostly constant in intensity, there are micro variations due to the granulation, convection, and occasional flares or bright points. Even these small changes are meaningful. They carry information about the processes inside the star, the transfer of energy from core to surface, and the movement of plasma within magnetic fields. Observing these fluctuations trains the eye or sensors to detect patterns that reveal the internal workings of this immense object. From this approach, it is possible to estimate the star's age. Its color, temperature, size, and surface activity all contribute to a precise understanding. This is a massive star, several hundred million years old, evolved beyond its early phases. Its mass has determined its current radius and luminosity. Approaching it closely allows you to see the balance between gravitational collapse and internal pressure from fusion. The surface is stable in the sense that it does not change drastically from day to day, yet it is in constant motion, a careful equilibrium between enormous forces. Continuing your approach, you begin to perceive the faint shimmer at the edges of the visible disk. Limb darkening is stronger in some regions, weaker in others, reflecting local temperature variations. Bright points and faculae emerge, slightly hotter and more luminous areas scattered across the photosphere. These bright points are temporary, changing on the timescale of minutes or hours, yet their presence contributes to the texture of the star's visible face. Observing them gives insight into convection, magnetic activity, and surface dynamics, all from this first close approach. Finally, as you complete this initial segment of flight around the star, you take in the full impression. This is an immense, active, and structured object. Its size is staggering, its surface alive with motion, and its light carries information about every layer beneath and above. Even without touching it, you can sense the scale, the energy, and the complexity of this star. The observation prepares you for a closer inspection, for moving past the photosphere into the layers above, where the dynamics of plasma, magnetic fields, and energy transfer reveal even more about the life of the largest star ever observed. Now we move closer to the star, entering the zone of its visible surface, the photosphere. At this distance, the star is no longer just a glowing ball in space. Its surface shows detail, subtle patterns that shift and change constantly. The photosphere is where most of the light we see originates. It is not a hard surface, but a dense layer of gas. The gas is hot, moving in slow, rolling currents. These currents create granules, roughly the size of continents on Earth, where hot material rises and cooler material sinks. The tops of the granules glow brighter because they are hotter, while the edges are slightly dimmer. These patterns are in constant motion, forming a living mosaic that changes every few minutes. Each granule is powered by convection. Deep within the star, energy produced in the core pushes outward. When it reaches the outer layers, the gas becomes unstable. Hot plasma rises, carrying energy to the surface. As it cools, it sinks back down, forming the dark edges of granules. Observing these motions, you see a rhythm, subtle but persistent. The brightness across the surface is uneven. Some regions appear slightly lighter or darker, responding to local temperatures and flows of material. The variations are small, yet they provide clues about the strength of convection and the energy moving beneath the surface. Temperature is central to what you see. The photosphere of this star is extremely hot, though cooler than the core. Its surface averages tens of thousands of degrees Celsius, enough to produce the intense light and radiation that reaches your sensors. Even without direct measurement, you can tell the differences in brightness correspond to temperature differences of thousands of degrees. Areas that shine more intensely indicate rising hot plasma, while dimmer areas show cooler, sinking material. Watching these changes in real time creates a sense of motion across the entire sphere, like observing clouds moving across a planet, but with far more energy and scale. In addition to granules, the surface displays larger patterns. Supergranules exist, covering hundreds of thousands of kilometers. These structures last longer than individual granules, sometimes for a day or more. Their edges are marked by narrow lanes where cooler gas sinks, and within them, the rising hot gas forms a network of brighter regions. Observing this network shows the complex flow of energy across the photosphere. Even in this single layer, there is a rich and intricate interplay of motion, temperature, and brightness. The color of the surface is affected by these dynamics. While the star appears pale yellow at a distance, up close you see subtle variations. Some areas take on a slightly orange hue, others almost white. The differences are small, but they indicate temperature changes, density variations, and the composition of the plasma. Light scattering within the gas also contributes, softening the edges of granules and blending colors gently. Moving across the surface, the eye or instruments can detect this gentle patchwork, shifting slowly but continuously. Observing movement is essential. Individual granules last only a few minutes, rising and falling in a continuous cycle. As they fade, new granules form in nearby locations. This turnover is relentless, yet never chaotic. The flow is structured by the energy coming from beneath and the star's rotation. Differential rotation also shapes the surface. The equator spins faster than the poles, stretching surface features along lines of latitude. Over time, you can see patterns elongate and shift, adding another dimension to the slow dance of plasma. Sunspots, or star spots in this context, become visible. These are regions where strong magnetic fields inhibit convection. The result is a cooler area that appears darker than its surroundings. Star spots vary in size, some thousands of kilometers wide. They are not static. They form, grow, shrink, and dissipate. Observing these features provides insight into the star's magnetic activity and internal flows. Though darker, they are still intensely bright compared to any sunlight on Earth. Their presence introduces contrast across the photosphere, breaking the uniformity of granules and supergranules. Bright regions appear near sunspots. These are called faculae, slightly hotter areas that emerge along magnetic field lines. They brighten the surface subtly, contrasting with the darker star spots. Faculae are short-lived but frequent, and they add to the dynamic texture of the photosphere. Watching them flicker and shift gives a sense of the constant energy movement, the magnetic fields shaping the gas, and the complexity of the star's outer layers. The photosphere also produces oscillations. These are waves of pressure moving through the gas, causing the surface to rise and fall gently. The changes in height are small, only a few hundred kilometers, but across the expanse of the star, they influence the patterns of light and motion. Observing the oscillations, you see rhythmic pulsations, almost like a slow heartbeat. They are measurable and provide information about the star's internal structure, allowing scientists to infer conditions in layers far below what is visible. The interplay of light and shadow is subtle but constant. As plasma rises and sinks, brighter regions and dimmer lanes shift gradually. The effect is never static and never abrupt. It is a continuous flow, a shifting mosaic of heat and energy. Watching this over time, You develop an intuitive sense of the star's surface behavior, understanding how energy moves, how material rises and falls, and how the magnetic field shapes these motions. The photosphere is the gateway to the star's atmosphere. Above it, the gas becomes thinner, forming the chromosphere and corona. From this distance, you notice the base of this transition. Wisps of gas extend slightly above the main visible surface. Their color and brightness differ from the photosphere, more subtle and diffuse. They are shaped by the star's magnetic field and by the motion of the plasma below. Even in these outer edges, you can detect movement indicating the flow of energy into higher layers. Rotation affects how you see the surface. The differential rotation causes features to drift slowly in longitude. From pole to equator, the speed differs, subtly stretching or compressing patterns. Observing the same granules over time, you can detect the shift, noting how the surface evolves. Some patterns move faster than others, following currents in the plasma rather than strictly following the rotation. The result is a complex choreography of motion across the photosphere, always changing, yet governed by predictable physical laws. The intensity of light varies with local activity. Areas near faculae, or active regions, shine slightly brighter. Cooler lanes between granules appear dimmer. These differences are small but detectable. By studying them, you gain insight into the energy transport mechanisms, the efficiency of convection, and the influence of magnetic structures on surface brightness. Each variation tells a story about the processes occurring just beneath the visible layer. From a distance, the photosphere might seem calm. Up close, it is in constant motion, a dynamic sheet of plasma with energy rising and falling, bright and dark patches forming and dissipating, magnetic fields shaping flows, and subtle oscillations causing gentle pulsations. Observing these details provides a sense of scale, activity, and structure that is otherwise impossible to grasp. Every glance reveals something new, even over short periods of time, highlighting the complexity of this largest star ever observed. The surface patterns are not random. Convection follows principles of physics, rising where the plasma is hot, sinking where it cools. Magnetic fields interact with these motions, sometimes inhibiting flow, sometimes channeling energy into bright regions or star spots. The interplay is subtle and continuous, creating a mosaic of activity that never repeats exactly, yet always follows the rules dictated by temperature, pressure, and magnetism. Even the dimmest regions carry energy. The entire photosphere is active, each square kilometer a site of motion, heat transfer, and light emission. Observing these regions over time, you can see faint, bright points emerge as material rises, then fade as it cools. This process happens millions of times across the surface simultaneously. The overall impression is of a calm but ever changing sphere, not still, not chaotic, but alive with movement governed by natural forces. Watching from different angles, you notice the three-dimensional structure of granules and supergranules. Light reflects slightly differently, depending on curvature and viewing angle. Some regions appear elongated, others compressed. The effect is subtle, but reinforces the sense of depth. Even without touching the star, the visual cues provide information about density gradients, flow speed, and orientation of convection cells. As you continue to observe, the variations in color and brightness become more apparent. The pale yellow of the photosphere has subtle gradients. Areas influenced by upwelling plasma are slightly whiter. Areas with cooler sinking gas are faintly orange. The blending of these shades is continuous, never abrupt. Tracking these changes over minutes reveals patterns in motion and energy transport that are key to understanding the behavior of this enormous star. Finally, as this first close study of the photosphere concludes, you are left with an impression of complexity and balance. The surface is dynamic, structured, and informative. Every feature, from the smallest granule to the largest supergranule, carries meaning about energy transfer, convection, magnetic fields, and the star's internal processes. Observing it closely prepares you for the next stage of the journey, moving above the photosphere into the outer atmospheric layers where new patterns and dynamics await discovery. Moving outward from the photosphere, we enter the star's atmospheric layers. This region is less dense than the visible surface, but it is still filled with motion, energy, and light. The first layer above the photosphere is the chromosphere. It is a thin layer in comparison, yet it stretches thousands of kilometers above the surface. Its temperature is higher than the photosphere, and it glows in subtle shades of red and pink, mostly visible in certain wavelengths of light. The chromosphere is made mostly of hydrogen, with traces of helium and heavier elements. Gas in this layer is less dense than below, but it is highly active. You can see spicules, narrow jets of plasma, rising and falling in rapid motion. These structures are short lived, lasting only a few minutes, yet they cover the entire star's surface at any given time. The chromosphere is dynamic. Most plasma rises where magnetic activity is strong, then falls back down, creating a shifting texture of vertical motions. Waves of energy move through the gas, carrying heat upward. Some of these are acoustic waves, caused by pressure changes in the lower layers, while others are magnetic waves, shaped by the star's complex magnetic field. Observing these motions, you get a sense of the energy transfer occurring. Heat moves from the surface upward, guided and accelerated by the magnetic structures that thread the chromosphere. Above the chromosphere lies the transition region. This is an extremely thin layer, only a few hundred kilometers thick, but it marks a dramatic change. The temperature rises sharply here, reaching hundreds of thousands of degrees Celsius. This sudden heating is not fully understood, but it is related to magnetic activity and the movement of charged particles from below. From this vantage point, you can see the gas becoming more diffuse, less structured than the photosphere or chromosphere. Light emitted here is mostly in ultraviolet wavelengths, invisible to the human eye without instruments, but it carries essential information about density, temperature, and motion. The corona extends beyond the transition region, stretching millions of kilometers into space. It is extremely hot, with temperatures in the millions of degrees. Despite this heat, it is very thin, almost a vacuum compared to the layers below. The corona is shaped by magnetic fields rising from the star's surface, creating loops, arches, and bright points. Plasma follows these field lines, moving in curved paths over the surface. Observing, the corona gives a sense of the star's reach, the extent of its influence, and the scale of energy moving outward. Even from a distance, the corona is enormous, extending far beyond the visible surface, and it is in constant motion. Energy moves outward through those layers in multiple ways. Radiation from the photosphere penetrates the chromosphere, but much of the heat is carried by convection and by waves in the plasma. Magnetic activity shapes these motions, trapping charged particles in loops and accelerating them along field lines. The result is a continuous, flowing movement of energy, heat, and light. You can observe the slow rise of plasma along magnetic arches, then watch as it cools and falls back, tracing paths that span thousands of kilometers. Spicules in the chromosphere are constantly forming and disappearing. Each one rises with speed, reaches a peak, and then descends. Millions of these jets occur at any moment, creating a shifting, complex layer above the surface. Their motion is guided by magnetic fields and pressure differences. Observing them from this perspective, you can see the energy carried upward, connecting the dense surface to the more rarefied outer layers. The chromosphere is alive with these flows, each small movement part of the larger process of energy transport. The transition region's thinness makes it difficult to observe directly. Its temperature jumps dramatically from the cooler chromosphere to the extreme heat of the corona. The density drops sharply, and the gas becomes highly ionized. Light emission is concentrated in specific ultraviolet lines, giving information about temperature gradients and plasma composition. From your point of view, this layer feels like a sudden boundary, marking the shift from the relatively calm chromosphere to the violent, energetic corona. It is a place where energy concentrates, accelerates, and begins to escape into space. The corona itself is structured by magnetic fields. Loops rise from the surface, arching over active regions, tracing paths hundreds of thousands of kilometers long. Plasma moves along these loops, sometimes slowly, sometimes quickly, depending on local conditions. Bright points mark regions of intense magnetic activity. Observing the corona, you notice the contrast between dense loops and open regions where plasma streams outward freely, forming the stellar wind. The corona is enormous compared to the star's surface, and its shape is constantly changing, influenced by rotation, magnetic cycles, and flares. Coronal mass ejections are sudden events in the outer layers. Large amounts of plasma can be ejected into space along magnetic field lines. These events release energy equivalent to billions of nuclear bombs. From this observational distance, you can detect the movement of these clouds of plasma, see them expand, and trace their path into space. Even though rare on the scale of the star's lifetime, each event reshapes the surrounding magnetic and plasma environment, creating transient structures in the corona. The star's magnetic field is visible through the motion of plasma in the chromosphere and corona. Loops and arches trace the field lines, and their shape reveals areas of stronger or weaker magnetic strength. Active regions are marked by dense, bright loops, while quieter areas have more open structures. Plasma movement along these lines carries energy from the surface outward, allowing heat to rise and escape into space. Observing this motion creates a sense of depth and scale, showing the star not as a simple sphere, but as a complex, energetic object shaped by invisible forces. Light emitted from these layers varies by wavelength. The chromosphere shines in red light, mostly hydrogen emission. The transition region emits ultraviolet radiation, giving insight into the rising temperature. The corona emits an X-rays indicating the extreme heat and low density. By observing these emissions, you gain a full understanding of the energy distribution, the movement of plasma, and the effects of magnetic activity across layers. Each wavelength provides a different view, but together they show the star's atmosphere in continuous motion. From your viewpoint, the scale of these layers is enormous. The chromosphere stretches thousands of kilometers above the photosphere. The corona reaches millions of kilometers into space. Even a single loop of plasma in the corona can be longer than the distance between Earth and the Moon. Watching the flow of energy through these layers gives a tangible sense of the star's size and power. Plasma rising, cooling, falling, and moving along magnetic lines is visible across this immense stage, a constant movement of material and energy. Temperature contrasts are striking. The photosphere is tens of thousands of degrees, the chromosphere hotter still, and the corona reaches millions of degrees. The mechanisms of heating are different in each layer. In the chromosphere, convection and waves dominate. In the transition region, the temperature rises rapidly due to magnetic processes. In the corona, magnetic reconnection, waves, and particle acceleration maintain extreme temperatures. Watching the energy move outward demonstrates how the star sustains these conditions over vast scales. The corona is the source of stellar wind. Plasma escapes along open magnetic field lines, moving outward at high speeds. This flow carries mass and energy into space, shaping the local environment and interacting with any surrounding material. Observing this from a close approach, you can see the speed and direction of these flows, the density of particles, and the structure imposed by magnetic fields. Even without feeling it, the motion is perceptible in the patterns of light and plasma density. Active regions on the surface and influence the atmosphere above. Sunspots anchor magnetic loops that rise into the chromosphere and corona. Energy stored in these fields drives motion in the plasma, creating bright arches and jets and localized heating. The coupling between the surface and outer layers is continuous. Nothing happens in isolation. Every movement in the photosphere affects the layers above, and every loop of plasma is a bridge carrying energy outward. Rotation also shapes the atmosphere. Differential rotation stretches loops and twists field lines. This twist can store energy, which is released later in flares or eruptions. Watching the slow rotation and the resulting deformation of structures in the chromosphere and corona provides insight into the forces at work. Even at the largest scale, movement is predictable yet never static, revealing the dynamic balance of the star's outer layers. Finally, observing the combined layers, you sense the scale of energy moving outward, from the photosphere through the chromosphere and across the transition region and into the corona. Energy rises, guided by convection and magnetic fields, shaping plasma, radiation, and motion. The atmosphere is structured yet dynamic, thin yet vast, and constantly changing. Each movement, each pulse of plasma, carries heat and light into space, showing the living processes that sustain this immense star. From this perspective, the star is no longer just a glowing sphere, but a fully realized system, layers of energy in motion, structured by physics and shaped by forces visible and invisible alike. Turning our attention to the star's magnetic activity, we begin to observe the regions where star spots appear. Star spots are areas on the surface that are cooler than their surroundings. On a star of this size, these spots can be enormous, sometimes hundreds of thousands of kilometers across. They are visible as darker patches against the bright photosphere. Even though they are cooler, they still emit incredible amounts of light and energy. Observing them closely, you can see their shape and structure. The edges are irregular, not smooth, and small bright points sometimes appear within them, indicating localized heating. The darker color indicates that the intense magnetic field in these regions is inhibiting convection, preventing the hot plasma from rising as freely as it does in surrounding areas. These star spots are connected to the magnetic field lines of the star. Magnetic fields emerge from the surface, arch over the star, and re-enter elsewhere, creating loops that can stretch tens of thousands of kilometers into the atmosphere. The loops trap plasma, guiding its motion along the field lines. Watching the plasma follow these invisible paths, you can see how magnetic activity shapes both the photosphere and the layers above. Some loops are stable for hours or days, while others change rapidly, expanding and twisting, and sometimes breaking apart. Flares are sudden releases of energy that occur near these active regions. When magnetic field lines reconnect or shift, they can release vast amounts of energy in the form of light, heat, and charged particles. From our point of view, flares appear as brief, intense brightening in localized areas. Even in the presence of a flare, the surrounding surface remains relatively calm. The contrast between sudden bursts of energy and the steady glow of the rest of the photosphere is striking. Each flare carries information about the star's magnetic field, the amount of energy stored in it, and the dynamics of plasma trapped along loops. Prominences are another feature of magnetic activity. These are large arcs of plasma that rise from the surface, held in place by magnetic fields. They can extend hundreds of thousands of kilometers, curving gracefully above sunspots or active regions. The plasma within a prominence is cooler than the surrounding corona, and its motion follows the structure of the magnetic field. Observing prominences provides insight into how magnetic energy moves from the surface into the outer layers. The loops are dynamic, sometimes collapsing or erupting, releasing material into the surrounding space. Long-term cycles shape the appearance of star spots. On stars like this one, magnetic activity waxes and wanes over years or decades. Star spots appear in bands at certain latitudes, then migrate over time. The number and size of spots fluctuate, creating periods of high and low activity. Observing these changes over months or years reveals the rhythm of the star's magnetic life. High activity periods bring larger and more numerous spots, more frequent flares, and stronger prominence activity. Low activity periods show fewer spots, more uniform brightness, and calmer atmospheric conditions. The contrast between calm regions and active areas is significant. Some parts of the photosphere are nearly uniform, with smooth granulation and gentle convection. Nearby star spots and bright faculae introduce strong local variations. Observing this contrast helps you understand how magnetic fields influence energy transport, surface brightness, and plasma motion. Even subtle differences are meaningful, revealing the structure of magnetic networks that extend from the surface into the outer layers. Magnetic field lines themselves are invisible, but their presence is made clear by plasma motion. Bright plasma traces the shape of loops, and moving features follow curved paths along these lines. Observing the motion over time shows the tension and stress within the magnetic field. Twisting, stretching, and reconnecting lines indicate regions of energy storage. Sudden releases, in the form of flares or eruptions, show how this energy can escape, reshaping the local environment. The size of star spots on this star is immense. Some cover a significant fraction of the visible surface. These giant spots can persist for weeks, while smaller ones appear and fade more quickly. Their formation and evolution are dictated by the underlying magnetic field and the flow of plasma in the convective zones below the surface. By tracking these spots, you can see the rotation of the star, differential motion across latitudes, and the movement of active regions over time. Flares vary in intensity. Small flares cause slight brightening near a spot, while massive flares can release energy equivalent to billions of nuclear explosions. Observing a flare, you see the rapid expansion of plasma, brightening along loops, and the outward motion of charged particles. The surrounding atmosphere reacts, waves propagate through the corona, and the local magnetic field reorganizes. Flares provide a vivid demonstration of the energy stored in magnetic structures and the way it can be released suddenly. Prominences can be stable or eruptive. Stable prominences maintain their shape for hours or days, their plasma tracing long arcs above the star's surface. Eruptive prominences break apart, releasing material into the corona or even beyond, contributing to stellar wind and reshaping local magnetic structures. Observing these events reveals how the magnetic field contains and directs the movement of plasma over vast scales. The interplay between spots, faculae, flares, and prominences is complex. A single star spot may anchor multiple loops, some bright, some dark, guiding plasma in different directions. Nearby, faculae enhance brightness, adding contrast. A flare may erupt, sending energy into the surrounding loops, sometimes triggering additional activity nearby. The star's surface and atmosphere are linked in a continuous feedback loop where magnetic activity drives motion and motion reinforces magnetic structures. Differential rotation affects magnetic patterns. The equator rotates faster than the poles, stretching and twisting magnetic field lines. This motion can lead to increased energy storage, eventually released as flares or eruptions. Tracking rotation across different latitudes shows how spots drift. Loops shift, and prominences change orientation over time. The combination of rotation and convection produces a constantly evolving magnetic environment. Magnetic cycles are predictable on long timescales. Over years, the star experiences periods of high and low activity. These cycles influence the number, size, and distribution of star spots, the frequency of flares, and the structure of prominences. Observing a full cycle provides insight into the star's internal dynamo, the mechanism that generates and maintains magnetic fields. Even subtle changes in activity can affect the outer atmosphere, plasma flow, and energy transfer into space. Observing active regions from different angles reveals depth and structure. Loops curve above spots, connecting different areas. Flares erupt at specific points along the loops, releasing energy that ripples outward. The chromosphere and corona respond, with plasma shifting along field lines. The complex three-dimensional structure is visible, showing how magnetic forces shape the star beyond the surface. Brightness varies across the star due to magnetic activity. Star spots appear darker, faculae brighter. Surrounding regions may remain stable, but small changes in brightness indicate shifts in magnetic energy. Tracking these variations allows you to map the magnetic network and understand the flow of energy. Even without measuring field strength directly, the surface features tell the story of the star's invisible forces. The largest star spots sometimes dominate entire hemispheres. They anchor huge magnetic loops, stretching far into the corona. Observing them highlights the scale of magnetic influence, the size of energy structures, and the connection between surface and outer layers. Plasma follows the field lines, flares erupt, and prominences form along these loops, demonstrating the interplay of heat, motion, and magnetic control. Sudden activity contrasts sharply with calm regions. While much of the photosphere remains gently convective, flares, loops, and prominences introduce localized bursts of energy. This contrast is informative, showing where magnetic stress is greatest, how energy is stored and released, and how the star balances calm and activity. Each feature contributes to the overall structure, creating a dynamic, constantly changing surface and atmosphere. By observing these features, you gain insight into the life of the star. Star spots, faculae, flares, and prominences are not random. They follow patterns dictated by rotation, convection, and magnetic cycles. Their appearances, evolution, and disappearance provide clues about the internal workings of the star, the distribution of energy, and the forces that shape both surface and atmosphere. Over time, these observations form a coherent picture of the star as a living, active system, its magnetic field a defining force in its behavior. Turning our attention to the star's rotation, we begin to notice how movement shapes its form and surface. Unlike a rigid object, a star is a ball of gas and plasma held together by gravity. This means rotation affects the entire body differently than would a solid sphere. The equatorial regions spin faster than the poles, a phenomenon known as differential rotation. As a result, the star is not perfectly round. The equator is slightly wider than the polar regions, forming a gentle bulge. From our perspective, the curvature along the equator is less steep than near the poles. This bulging is subtle, but when viewed over the star's immense diameter, it is measurable and significant. Observing the surface, you notice that patterns shift at different speeds, depending on latitude. Granules near the equator drift more quickly along the rotation direction, while those closer to the poles move slower. Star spots, loops, and faculae follow this motion. A spot near the equator completes a rotation faster than a spot at mid-latitudes. This differential motion stretches magnetic field lines over time, influencing the formation of flares, prominences, and surface activity. The combined effect of rotation and convection creates a continuously evolving surface, where motion and magnetic structures interact in complex ways. The equatorial bulge affects how energy is transported across the star. The surface gas at the equator is slightly farther from the center of mass, meaning the pressure and gravitational pull vary across latitudes. This subtle difference influences convection patterns, causing granules near the equator to be slightly larger and more elongated than those near the poles. Observing these changes, you can see how rotation shapes the dynamics of rising and sinking plasma, reinforcing the idea that motion and structure are closely linked. Rotation also affects the appearance of star spots. A spot at the equator moves along the surface faster, appearing to drift past your viewpoint more quickly than spots at higher latitudes. Over time, You can track this motion, noting the relative speeds and observing how the rotation stretches or compresses magnetic loops. Bright regions and flares follow the same pattern, revealing the coupling between surface motion and magnetic activity. Differential rotation is a driving force behind many phenomena observed on the star. Watching from a distance, the overall shape of the star is slightly oblate. The equator appears broader, the poles more compact. This effect is small compared to the star's total size, yet it is measurable. Observing how the light curves along the equator versus the poles reveals these subtle differences. The variation in radius affects surface gravity slightly, which in turn modifies the motion of plasma, influencing convection and the stability of magnetic structures. Even small differences in force and distance have noticeable effects across the enormous scale of this star. Surface patterns provide visual cues about rotation. Granules near the equator move with a gentle lateral drift that is faster than granules at higher latitudes. Supergranules follow the same trend. Star spots also provide markers. By tracking their movement over time, you can determine rotation speed at various latitudes. These measurements are important for understanding the internal dynamics, the distribution of magnetic activity, and the evolution of surface features. Observing motion on this scale gives a sense of both the speed and the rhythm of the star's rotation. Rotation interacts with magnetic fields to influence the corona and outer layers. Twisting field lines at different latitudes can store energy, which is later released in flares or prominences. Plasma follows these lines, moving at speeds influenced by both rotation and magnetic tension. Observing the flow of material along loops reveals how differential rotation affects energy transfer from the surface outward. The outer atmosphere is shaped as much by rotation as by the internal dynamics of the star. Equatorial bulging also affects light emission. Because the equator is slightly farther from the center, the line of sight passes through different layers of the star's atmosphere, subtly altering brightness and spectral lines. Limb darkening varies slightly with latitude, providing a visual cue that the star is not perfectly spherical. By studying these variations, you gain a more complete understanding of the star's rotation, structure, and surface dynamics. The interplay between shape, rotation, and light is subtle but informative. The rotation period varies with latitude. Near the equator, the star may complete a full rotation in days, while higher latitudes take longer. This difference creates shear, stretching magnetic structures and influencing the formation of active regions. By observing surface motion over time, you can map the distribution of rotation speeds and understand how the star maintains its magnetic activity. Differential rotation is a key factor in shaping the star's dynamic behavior. Granules and supergranules provide ongoing markers for motion. Near the equator, the rising and sinking plasma follows a drift faster than at the poles. This means convection patterns stretch and twist along the rotation direction. Star spots follow the same trend, showing relative motion depending on latitude. Bright faculae move similarly, emphasizing the large-scale impact of rotation on the visible surface. Observing these motions in real time conveys a sense of scale and complexity. Rotation influences flares and prominences indirectly. When magnetic loops are twisted by differential motion, energy can build up. Eventually, reconnection occurs, releasing energy in sudden bursts. The location, size, and intensity of flares are shaped by the rotation-driven deformation of magnetic structures. Prominences rise along loops that are affected by latitude-dependent motion. Watching the outer layers respond to rotational effects demonstrates the interconnectedness of surface dynamics and atmospheric activity. The star's shape also affects plasma flow. At the equator, the slight bulge means the surface is farther from the core, so plasma experiences a marginally weaker gravitational pull. This modifies convection speed and the size of granules. Near the poles, stronger gravity slightly compresses plasma motion. These small differences become noticeable when observing large scale flows and magnetic loops, highlighting how rotation and shape together influence the behavior of the star's outer layers. Differential rotation produces shear zones. These are areas where the equatorial surface moves faster than adjacent latitudes. The shear stretches granules, supergranules, and magnetic structures. Observing these zones shows patterns of tension in the plasma, where loops can twist or break. Over time, shear influences the distribution of star spots, the frequency of flares, and the formation of prominences. The continuous effect of rotation is apparent at every scale, from small plasma cells to massive magnetic structures. The motion of features provides visual rhythm. Granules drift laterally at different speeds depending on latitude. Star spots trace arcs across the surface, some fast, some slow. Magnetic loops bend and twist, their plasma following the underlying motion. Prominences sway gently as they follow magnetic lines affected by differential rotation. This combination of movement gives a sense of continuous, ordered activity on the star, showing how rotation shapes the surface and atmosphere. Observing rotation from multiple angles reinforces understanding. From the poles, the equatorial bulge is less obvious, but differential motion is detectable. From the equator, bulging is more pronounced, and lateral drift of surface features is more visible. By comparing views, you can track both shape and motion, confirming the influence of rotation on surface dynamics and magnetic activity. The visual cues are subtle but consistent, allowing a detailed assessment of rotational effects. Rotation also affects long term magnetic cycles. Differential rotation twists field lines over time, influencing the emergence of star spots and active regions. Sheared loops store energy that eventually releases as flares or eruptions. By observing surface motion and magnetic activity together, you see how rotation sets the rhythm for longer cycles of activity. The interplay between motion, structure, and energy is continuous, shaping both the surface and the surrounding atmosphere. Finally, the overall impression of rotation and shape is one of subtle influence over enormous scale. The equatorial bulge is gentle but measurable. Differential motion stretches granules, star spots, and magnetic loops. Surface and atmospheric features follow the rotation, creating a dynamic, evolving star. Observing these patterns provides a clear understanding of how rotation shapes the star's behavior, influences energy transport, and interacts with magnetic activity. The star is not static. It spins, flows, and stretches, creating a living, moving system where shape and motion are inseparable. Through careful observation, you can appreciate both the speed and the scale. Rotation affects every layer, from the photosphere to the corona. Granules drift, loops twist, prominences rise and fall, and flares erupt along sheared lines. The combination of shape and differential rotation defines the star's surface dynamics, offering insight into its internal processes and the forces shaping its appearance and activity. The star's movement is constant, continuous, and intimately tied to the structure we observe, showing the importance of rotation in understanding this massive celestial body. As we move further from surface observation, our focus shifts to the radiation and light the star produces. The energy that rises from the core, carried through convection and convection related motion, ultimately escapes as electromagnetic radiation. This radiation spans a wide range of wavelengths, from infrared to visible light, ultraviolet, and beyond. Each wavelength tells a story about the processes taking place within and above the photosphere. Observing this radiation closely, you can sense gradients of brightness across the surface, subtle changes that correspond to temperature differences and atmospheric dynamics. Light spreads outward in every direction, carrying energy into space and influencing everything in the surrounding environment. The visible light is what dominates our perception. It emerges from the photosphere and is influenced by the movement of granules, the presence of star spots, and magnetic structures. Bright regions contribute more to the overall luminosity, while darker areas, such as star spots, slightly reduce the output locally. When viewed from a close perspective, the surface appears to glow unevenly, a mosaic of brighter and dimmer areas, each emitting vast amounts of energy. The interplay of brightness and shadow gives a subtle texture, a constant flow of energy rising from deep within. Beyond visible light, ultraviolet radiation plays a critical role. The chromosphere, transition region, and corona emit strongly in ultraviolet wavelengths. This light carries energy from the hotter outer layers into space. Unlike visible light, ultraviolet radiation cannot be seen directly, but its effects are measurable. It heats the surrounding plasma, drives photochemical reactions in nearby materials, and shapes the ionization of gas in the star's vicinity. From a viewing perspective, the presence of ultraviolet radiation is implied by the activity in these layers, the rising and falling plasma, and the bright points along magnetic loops. Infrared radiation is also significant. This light is associated with the slightly cooler outer layers and is emitted continuously. It spreads broadly across space and carries heat energy. Observing the infrared output, you sense the energy flow in a more diffuse way, a steady warming that complements the bright, focused, visible light. The combination of visible, ultraviolet, and infrared radiation provides a full picture of how energy escapes the star, moving outward to illuminate and influence surrounding space. Radiation interacts with nearby material in multiple ways. Photons collide with atoms, excite electrons, and can be absorbed or scattered. These interactions shape the local environment, creating regions of ionized gas, stimulating plasma movement, and contributing to the formation of stellar wind. Light does not just travel freely, it also imparts momentum and energy, subtly influencing the motion of gas and charged particles in the immediate space around the star. Observing these interactions, you sense that energy is not static, but dynamic, flowing outward in multiple forms simultaneously. Intensity varies depending on location. The areas above star spots may emit slightly less visible light, while faculae increase brightness locally. Bright loops in the corona emit ultraviolet light more intensely, revealing regions of high energy concentration. By tracking these variations, you can see where energy is most concentrated and how it is distributed across the surface and into the atmosphere. The combination of bright and dim regions creates a continuously evolving map of electromagnetic output. From the point of view of an observer, you sense a gradient of light and energy. The intensity changes gradually as you move across the surface and above the atmosphere. There is warmth in the sense of energy present, though at this distance it is a conceptual sense, not a physical danger. Subtle shifts in brightness, from dimmer lanes between granules to intense faculae, create a textured field of radiation. You perceive patterns of rising and falling energy, the flow from high energy ultraviolet to steady infrared and visible light, forming a complex yet continuous distribution of electromagnetic output. The light curves slightly across the surface. Limb darkening occurs naturally, making the edges of the visible disk slightly dimmer than the center. This is a result of the angle at which photons escape through the layers of gas. Near the center, light emerges directly from hotter layers, while at the edges, photons travel through more material, scattering and losing energy. Observing this effect, you see the gradual fading toward the limb, a soft gradient that contributes to the perception of depth and shape. Flares and active regions produce sudden increases in intensity. A flare can emit vast amounts of visible and ultraviolet light in seconds, temporarily outshining surrounding regions. Prominences and loops also radiate, often more strongly in ultraviolet. Observing these variations in real time provides a clear sense of the star's energetic behavior, contrasting the steady output from calm regions with bursts of localized emission. The overall light field is therefore both stable and dynamic, changing on multiple timescales simultaneously. The radiation extends outward into the surrounding space, filling it with energy. Photons travel from the surface through the chromosphere and corona, eventually reaching interstellar distances. Along the way, they interact with plasma and magnetic fields, contributing to ionization, heating, and motion. This outward flow of energy is continuous and vast, extending far beyond the star's visible boundaries. And from a close observational perspective, you sense the reach of the star's output, a continuous stream that diminishes slowly with distance, but carries influence far into the surrounding environment. Different wavelengths provide different information. Visible light shows the surface structure, granulation, and brightness variations. Ultraviolet light indicates hotter regions in the outer layers and magnetic activity. Infrared traces more diffuse energy from cooler regions. Observing all three together creates a comprehensive understanding of the star's electromagnetic output, revealing patterns of energy transport, plasma motion, and magnetic influence. Each wavelength contributes to a holistic view, and together they define the star's radiative footprint. Intensity changes are gradual, not abrupt, except during flares. As plasma rises and falls in the chromosphere or corona, brightness adjusts slightly, creating a subtle pulsing effect. These variations are continuous, perceptible over minutes or hours. Observing the surface over time allows you to map the flow of energy, noting which areas emit more intensely, which are cooler, and how magnetic structures guide the movement of radiation. The light interacts with any nearby dust, gas, or material. Scattering and absorption occur naturally, shaping the environment around the star. This interaction influences the distribution of heat and light, forming areas of enhanced ionization, heating, and motion in the surrounding medium. Observing these effects provides a sense of the star's influence beyond its immediate surface, demonstrating the reach of radiation and its capacity to shape space around it. Brightness varies with altitude above the surface. Close to the photosphere, light is intense and directional. Moving outward into the chromosphere and corona, ultraviolet and X-ray emissions dominate, and brightness spreads more diffusely. This gradient is perceivable in instruments and can be imagined in terms of changing intensity from bright, structured surface patterns to faint, widespread radiation in the outer atmosphere. Observing this vertical gradient shows how energy is distributed through the layers before it escapes into space. The combination of radiation types forms a continuous layered output. Visible light dominates close to the surface, ultraviolet radiates from the outer layers, and infrared emerges from cooler regions. All of these travel together, forming a dynamic multi-wavelength field. By perceiving the gradients in intensity, you gain a sense of how energy moves from the interior through the surface and into the atmosphere, eventually leaving the star to influence the broader space environment. Overall, the star's electromagnetic output is both immense and structured. Brightness varies across the surface, pulses with flares, and extends outward through the outer layers. The viewer senses intensity changes, gradients of light, and directional patterns without danger, understanding the scale of energy moving outward. Radiation connects the surface, the atmosphere, and nearby space, providing insight into the processes sustaining the star's luminosity, magnetic activity, and overall energetic presence in the surrounding region. Even from a close perspective, the sheer scale of light emission is humbling. Every granule, Star spot and magnetic loop contributes to the total output. Photons of different energies travel along various paths, interacting with plasma and magnetic fields, shaping local conditions and contributing to the global distribution of energy. Observing these processes gives a sense of the continuous, flowing power of the star, a vast system where light, heat, and motion are inseparable and constant. The gradual fading of intensity toward the edges, the pulsing of brightness with activity, and the directional nature of emission together create a perceptible sense of energy flow. From a point of view immersed near the star, you can sense both the steady output and the intermittent bursts of activity. This combination forms a living, dynamic field of radiation, constantly replenished by processes deep within the star and shaped by the complex interactions of plasma, magnetic fields, and surface structures. By focusing on radiation and light, you understand how the star communicates energy to its surroundings. Every photon, from infrared to ultraviolet, carries information about temperature, motion, and magnetic activity. The interplay between wavelengths, brightness gradients, and energy flow provides a continuous, observable record of the star's processes. The outward stream of radiation illustrates how energy produced in the core moves through layers, escapes into space, and interacts with the environment, giving a tangible sense of the star's presence and influence beyond its visible surface. Moving outward from the star, we enter the space immediately surrounding it. Here, the energy released from the surface and outer layers meets the vacuum beyond, and matter itself begins to flow outward. One of the main features in this region is the continuous stream of particles that's known as the stellar wind. This wind is composed mostly of electrons and protons, moving away from the star at high speeds. It originates from the hot outer atmosphere, primarily the corona, where gas is heated to millions of degrees. Observing this wind, you notice it spreads evenly in all directions, carrying energy and material outward into space. The density of the wind decreases with distance, yet even far from the star, it carries momentum and can interact with anything it encounters. Coronal mass ejections are occasional, large-scale releases of plasma and magnetic fields from the corona. Unlike the steady stellar wind, these events occur irregularly and can release billions of tons of material into space. From a viewing perspective, a coronal mass ejection appears as a huge bubble or loop of glowing plasma rising above the star, expanding rapidly and moving outward. The eruption is guided by magnetic field lines, which determine the path of the material. As it travels, the ejected plasma moves at high speeds, interacting with the surrounding wind and magnetic environment. These events demonstrate the dynamic nature of the star's outer layers and the forces that shape nearby space. Plasma motion in this region is continuous, even between large eruptions. Charged particles follow the magnetic field, forming spirals and arcs as they move outward. The field is shaped by the star's rotation, differential motion, and previous activity. Observing these patterns, you can see both steady flow and turbulent regions where field lines twist or reconnect. This creates a complex environment where energy is transported outward along with matter. The motion is smooth in some regions and chaotic in others, reflecting the combined influence of magnetic forces and particle flow. The stellar wind and ejected plasma interact with the interstellar medium. When particles collide with gas and dust in nearby space, they transfer energy, ionize atoms, and can create waves or shock fronts. These interactions extend the star's influence far beyond its immediate atmosphere. Observing from a distance, you can detect subtle shifts in particle density, magnetic fields, and energy distribution. The region is not empty. It is filled with moving material that carries the signature of the star's activity outward through space. Magnetic fields in surrounding space guide the motion of plasma. Particles follow the curvature of field lines, forming streams and loops that extend far beyond the visible surface. When field lines twist and reconnect, energy is released, accelerating particles and creating bursts of activity that ripple outward. Observing these motions, you perceive both order and chaos. Streams of particles follow predictable paths, while sudden eruptions introduce turbulence and unpredictability. Together, these elements define the dynamic environment around the star. The velocity of the stellar wind varies with origin and magnetic configuration. Some regions of the corona emit fast wind, with particles moving hundreds of kilometers per second. Other areas emit slower wind, which interacts with faster streams and forms complex boundaries. Observing these streams, you can see how they merge, compress, and sometimes create turbulent regions where particle density and energy fluctuate. This flow shapes the immediate space environment and forms the starting point for broader interactions with the interstellar medium. Coronal mass ejections carry embedded magnetic fields with them. These fields interact with the surrounding wind and any external material they encounter. As a result, the path of the plasma is influenced by both the star's magnetic configuration and the local environment. Observing the motion over time, you notice the loops expand, stretch, and sometimes fragment. The overall effect is a constantly evolving structure where material and magnetic energy move outward together. Particle density in the surrounding space decreases with distance, yet even thin plasma has a measurable effect. Collisions between particles, magnetic pressure, and interactions with photons create subtle waves and instabilities. Observing these phenomena, you can detect patterns in particle motion and energy transfer. The outward flow of plasma is continuous, shaped by both the star's activity and the surrounding conditions. Even far from the star, the material carries information about its origin, revealing details of the surface and atmospheric processes that generated it. The star's rotation affects the surrounding magnetic field. As the surface rotates, field lines are dragged along, forming spirals that extend into space. The outward moving plasma follows these spirals, creating a structured flow. In observing the pattern, you see how rotation combines with ejection events to shape the overall environment. The result is not uniform. Some regions are denser, others more diffuse, creating a varied and dynamic field that extends for millions of kilometers. Shocks and waves form where fast-moving plasma overtakes slower streams. These disturbances carry energy and can compress local particles, forming temporary heat density regions. Observing the motion, you notice subtle changes in brightness and structure as moving material interacts with itself. These waves propagate outward, gradually losing intensity, yet they demonstrate the continuous transfer of energy from the star into its surroundings. Ejected material often forms loops or arches guided by magnetic lines. A coronal mass ejection can stretch these loops to enormous distances, maintaining their structure while moving away from the star. The plasma within follows the magnetic contour, twisting and shifting as it expands. Observing from a safe perspective, you see the interplay of structure and motion, a dynamic ballet of energy and matter traveling outward. Stellar wind interacts with previously ejected plasma. Collisions between fast and slow streams create turbulence, enhancing mixing and redistributing energy. These interactions can form long-lasting features in the surrounding space, including density enhancements and regions of strong magnetic influence. Observing these patterns over time allows you to map the flow of material and the evolution of the star's immediate space environment. The influence of the star extends far beyond visible light. Plasma carries heat, momentum, and magnetic energy. These elements move through the surrounding space, affecting distant particles and gas. Observing the motion of these materials, you sense the connection between surface processes, magnetic activity, and distant effects. Each burst of material, each steady flow of the wind, is a continuation of the star's presence, extending influence outward in both energy and matter. At large distances, the flow becomes more diffuse, yet patterns remain. Streams of particles follow general paths dictated by magnetic structures and previous ejection events. Waves and turbulence persist, though intensity diminishes with distance. Observing these outer regions, you sense the scale of the star's influence, the continuous outward transfer of energy and matter, and the structured complexity of its surrounding space. The star's activity is a constant driver of change. Even when flares are not occurring, the wind moves outward steadily, carrying particles and magnetic energy. During more active periods, coronal mass ejections increase the flow, sending larger volumes of plasma into space. Observing these changes, you notice how the environment adjusts, how streams merge, and how magnetic fields rearrange. The star's behavior is reflected in the motion of surrounding material. Particles in motion interact with radiation as well. Photons from the star transfer momentum to electrons and ions, subtly influencing their paths. The combined effect of magnetic forces, particle motion, and radiation creates a layered and dynamic region around the star. Observing from a distance, you perceive gradients in density, speed, and energy, which reveal the structure of the star's extended influence. The surrounding space is not uniform. Fast streams from the corona push against slower streams and earlier ejections, forming shear zones and compression regions. Turbulent eddies appear where flows meet at angles, creating temporary regions of higher density and enhanced magnetic activity. Observing these areas provides insight into the forces shaping the environment and the continuing interaction between the star and space. Finally, observing at a distance, the particles appear to move as part of a larger, continuous flow. The wind, the coronal mass ejections, and the plasma streams are all part of a connected system, carrying energy, material, and magnetic influence outward. The star's activity is not limited to its surface. It extends far into space, shaping the environment and transferring information about the processes occurring within. The motions are measurable, perceptible, and continuous, giving a sense of the star's dynamic reach into its surroundings. Even at vast distances, the interaction between particles and fields remains apparent. Streams curve along magnetic lines, waves propagate, and turbulence continues. Observing these patterns, you gain a sense of scale and connectivity, understanding how material ejected from the star moves through space, interacts with itself, and gradually disperses. The star's influence is long-reaching, both in terms of matter and energy, and observing these motions provides a comprehensive understanding of the star's extended environment. Now we shift our attention to the star from a broader vantage point, observing it not only in itself, but also in relation to the larger galaxy it inhabits. From this perspective, you notice the star is not still. It moves along an orbit around the center of its galaxy, tracing a slow path influenced by the collective gravity of billions of stars, gas clouds, and dark matter. While the movement is gradual on a human timescale, over millions of years, it covers vast distances. Observing from our nearby position, we sense this motion as a subtle drift against the background of more distant stars. The star carries its entire system along, including any surrounding planets, asteroids, or diffuse debris. From this orbiting perspective, the relative motion of nearby objects becomes perceptible. Planets, if present, trace their own paths around the star, moving steadily in elliptical orbits determined by gravity. Their motion is much faster than the star's galactic travel, yet in this wide view, they appear to slowly circle, occasionally crossing paths with the observer's line of sight. Asteroids and smaller debris form scattered clouds or belts, moving with more variation. Their paths are less uniform, influenced by the gravitational pull of larger bodies, collisions, and the star's magnetic field. Observing these motions gives insight into the Structure and dynamics of the star's system. As we begin a slow flight around the star, the rotation becomes more apparent from different angles. Moving along the equator, the lateral drift of surface granules and star spots is observable. From this orbiting path, you can measure differential rotation more clearly, noting how the equatorial regions rotate faster than the poles. Star spots appear to drift, at varying rates, depending on their latitude, while prominences and loops above the surface follow the curvature of the rotation. Observing from multiple angles provides a richer understanding of the motion and structure of the star itself. Traveling over the poles, you perceive the star's shape differently. The equatorial bulge appears more pronounced from the side, confirming the oblate nature caused by rotation. Surface features near the poles move more slowly, creating a contrast with the faster equatorial drift. Magnetic loops and prominences stretch outward along predictable paths, showing the interaction of rotation and magnetic fields. Observing the star from multiple perspectives allows a three-dimensional appreciation of its structure, motion, and dynamic activity. The motion of surrounding material also becomes more noticeable from this vantage. Stellar wind flows outward continuously, carrying plasma along spiraling magnetic lines. Coronal mass ejections expand into space, their arcs and loops visible against the darker background. From a slow orbit, you can trace these movements as they extend away from the star, following the curvature of the magnetic field and interacting with previously ejected material. The combined effect is a layered, three-dimensional display of energy and matter moving outward. Planets and other orbiting objects provide additional context. As the observer traces a path around the star, the changing positions of these bodies reveal orbital planes and relative distances. Planets closer to the star move more rapidly, while those farther away progress more slowly along their paths. Their motion is predictable, yet the perspective shift highlights subtle variations in speed and alignment. Observing asteroids or small debris reveals a more chaotic component, with paths influenced by collisions or gravitational perturbations. This mixture of order and irregularity adds depth to the star's surrounding system. The star itself moves slowly relative to the galactic center. Observing nearby stars in the background, you notice a slight shift over time, a drift along the orbital path. The star carries its system along, yet the motion is subtle compared to the internal dynamics of the system. Planets, debris, and ejected plasma all follow the star's movement, forming a coherent yet dynamic structure. From this orbiting viewpoint, you can perceive the relationship between the star and the broader galactic environment. Flying slowly along the equatorial plane, surface motion and rotation are seen in a continuous sweep. Granules drift along the direction of rotation, star spots move at varying speeds, and magnetic loops rise and fall above the surface. Observing these features from a lateral path highlights the interaction of rotation, convection, and magnetic activity. From a different angle, the limb darkening at the edges of the photosphere becomes visible, providing subtle cues about the structure of the outer layers. When the flight path shifts over the poles, the observer perceives the full curvature of the star. The equatorial bulge is clearly evident, and the slower rotation near the poles is noticeable. Magnetic loops extend outward from high-latitude regions, occasionally connecting across the surface. Observing prominences from above or below gives a new understanding of their height and motion relative to the star's rotation. From this angle, you can see how features near the equator move faster, stretching magnetic structures and creating dynamic patterns in the surrounding atmosphere. The orbiting viewpoint allows observation of light and radiation from multiple angles. Bright regions, faculae, and star spots shift their appearance as perspective changes. Limb darkening and variations in intensity are more noticeable, providing visual cues about depth and structure. Ultraviolet and infrared emissions can be imagined extending outward, interacting with surrounding plasma and magnetic fields. Observing these gradients reinforces understanding of the star's energy output and the flow of radiation into space. Motion of nearby debris and minor bodies adds context to the orbiting perspective. Small objects trace unpredictable paths influenced by the star's gravity and magnetic activity. Collisions between debris can create temporary dust clouds, which slowly disperse. Observing these interactions over time highlights the dynamic nature of the environment surrounding the star. The star's gravity and magnetic influence extend beyond the surface, shaping the movement of all nearby material. From this perspective, coronal mass ejections become more apparent in three dimensions. Expanding loops of plasma rise above the surface, traveling along magnetic lines and outward into space. Observing from a lateral or polar path shows the curvature and height of these structures. Plasma follows twisted trajectories dictated by the magnetic field, sometimes interacting with the steady stellar wind. The orbiting viewpoint emphasizes the scale and motion of these ejection events relative to both the star and surrounding material. The orbit also reveals how rotation affects radiation. Bright areas move across the field of view at varying speeds, with equatorial regions sweeping by faster than polar areas. Star spots and magnetic loops appear to shift position, while light from faculae subtly enhances local brightness. Observing these changes over time gives a sense of continuous motion, with both energy and structure moving in relation to the observer's perspective. Even at larger distances, the observer can detect the flow of the stellar wind in previously ejected material. Streams follow spiraling paths influenced by rotation and magnetic fields, carrying both matter and energy outward. Observing from a slow arc around the star allows tracing of these flows in three dimensions, noting their structure, speed, and interaction with the surrounding environment. The combination of surface motion, radiation, and outflow creates a layered dynamic system observable from multiple perspectives. The slow arc around the star reveals the alignment of orbital planes for planets and debris. Inner planets move rapidly, with circular or slightly elliptical paths, while outer planets progress more slowly. Small bodies form belts or scattered orbits, their motion less regular. Observing these features gives a sense of the spatial scale of the system and the relative motion of objects influenced by the star's gravity and rotation. Rotation and motion combine to create perceptible patterns. From equatorial orbit, the faster rotation is apparent. From polar orbit, the bulge is visible, and the slower motion at higher latitudes is evident. Magnetic loops and prominences follow paths influenced by these rotations. The combination of orbiting perspective and direct observation of the star's surface allows understanding of motion, structure, and energetic processes as interconnected phenomena. As the observation continues, you notice subtle changes in relative positions. Planets, debris, and ejected material shift against the star's surface, highlighting the passage of time and the continuous motion of the system. Even in a slow, careful orbit, these motions are perceptible, illustrating both the immediate activity on the star and the larger scale dynamics of its surrounding space. From multiple angles, the star's behavior is evident in its light, rotation, and material ejection. Surface features drift, prominences rise and fall, radiation streams outward, and debris follows gravitational paths. The orbiting viewpoint provides a holistic sense of motion, connecting rotation, surface dynamics, radiation, and surrounding material. Observing in this way reinforces understanding of the star as a dynamic, three-dimensional object in constant interaction with its environment. Finally, the orbiting perspective allows appreciation of the star as both an individual body and a central component of a larger system. Its rotation, shape, radiation, and ejected material are all observable in relation to planets, debris, and galactic motion. By following slow arcs around the equator and poles, you gain a comprehensive understanding of motion and structure, seeing how the star functions in both local and broader contexts. The continuous observation emphasizes the dynamic nature of the system and the intricate interplay of energy, matter, and motion at multiple scales. Looking at the star over long time scales, you begin to sense the changes that occur gradually. Stars are not static, they evolve over millions and billions of years, and even a star of this size follows a predictable life cycle. From the point of view of our orbiting observation, the star remains visually constant day by day, but underlying processes are slowly reshaping it. The energy produced in the core, the balance between gravity and pressure, and the flow of material through convection all contribute to long term evolution. At the core, nuclear reactions gradually convert hydrogen into helium. This process is steady, but slowly changes the composition of the core. As hydrogen decreases, the core contracts slightly, increasing temperature and pressure. This affects the rate of fusion, gradually altering the energy output of the star. From a distant viewpoint, the surface luminosity may increase subtly over millions of years, though the change is imperceptible in the short term. Observing the star from orbit, you imagine this slow transformation, understanding that the steady light and rotation mask a long term evolution deep within. The outer layers respond to changes in the core. As energy output shifts, convection patterns adjust. Granules may change in size and duration, magnetic loops may alter their structure, and star spots can vary in size and frequency. Over extended periods, these adjustments reflect the star's internal rebalancing, a natural response to the slow change in core composition. Even if not immediately visible, these processes are continuously at work, maintaining equilibrium while guiding the star toward later stages of life. Rotation also evolves slowly. Angular momentum loss occurs as material is ejected through the stellar wind. The outer layers gradually slow, with equatorial rotation decreasing over millions of years. This change in rotation can influence magnetic activity, star spot frequency, and the structure of prominences. Observing the star from a steady orbit, you can imagine this gradual deceleration, the slow shift in motion that subtly changes how the star's energy and magnetic patterns interact. Magnetic activity and surface features also change over long periods. Cycles of activity continue, but their amplitude and duration may shift. Star spots and flares remain a constant presence, yet their frequency and size can evolve as the internal dynamo adjusts. Over millions of years, these changes influence the surrounding space, affecting the stellar wind, ejected plasma, and the broader environment of planets or debris. Observing the outward flow, you sense that even continuous streams are part of a long term story of evolution. The star's lifespan is determined primarily by its mass. A star of this size burns hydrogen at a specific rate, with fusion sustaining energy output for a finite period. As fuel diminishes, changes in luminosity, surface temperature, and radius occur. The star may gradually expand, cooling in its outer layers, becoming brighter in total output, but with a redder color. Observing the star over vast timescales, you imagine the transition from main sequence stability toward later stages, where size and temperature adjust slowly but significantly. Stellar evolution also affects surrounding material. Stellar wind gradually removes angular momentum and contributes to mass loss. Ejected plasma interacts with planetary atmospheres, debris belts, and any distant interstellar gas. Over millions of years, this flow reshapes the immediate environment, thinning some regions and enriching others. Observing from orbit, you can perceive the cumulative effects of long term ejections and wind on the surrounding system, a quiet transformation that mirrors changes within the star itself. Eventually, The star's core composition reaches a stage where hydrogen is largely depleted. Fusion shifts to helium burning, if conditions allow, creating new reactions and further altering energy output. Structural adjustments occur in the core and surrounding layers. The star may expand significantly, forming a larger radius with cooler surface temperature, and magnetic activity patterns shift in response. These changes mark the transition toward the final stages of the star's life. From orbit, these changes would manifest as subtle alterations in surface appearance, rotation dynamics, and the frequency of energetic events. Surface granules and convective patterns continue to evolve. As layers expand and temperature gradients change, convection becomes more pronounced in some regions and less in others. Bright and dark areas on the photosphere adjust, reflecting internal energy redistribution. Star spots may become larger or more irregular, and prominence activity can reach new heights. Observing the star during these transitions, you notice the subtle differences in motion, brightness, and structure that hint at the internal evolution taking place over millions of years. Radiation output changes gradually as well. Total luminosity may increase, even if surface temperature decreases slightly. The balance of visible, ultraviolet, and infrared emission shifts, reflecting changes in energy production and the structure of outer layers. The stellar wind may strengthen, carrying more mass outward and influencing the surrounding environment. Observing these adjustments from a slow orbit provides a sense of continuity, the star remaining recognizable while undergoing subtle, long-term transformation. As the star approaches the later stages of its life, more dramatic events may occur. Instabilities in the outer layers can lead to stronger ejections of plasma. Magnetic loops may reach greater heights, and flares can become more energetic. These events are the star's way of adjusting to changes in core pressure and energy output. From the observer's perspective, they appear as heightened activity across the surface and atmosphere, emphasizing the link between internal evolution and external phenomena. Planetary and debris environments are influenced over time as well. Gradual expansion of the star can alter gravitational dynamics, orbital distances, and material distribution. Radiation intensity changes impact atmospheres and surface conditions. Ejected plasma interacts with existing material, shaping belts, clouds, or rings. Observing from orbit, you see a system gradually adapting to the star's changing state, where motion, radiation, and magnetic influence continue to interact. Long-term evolution also affects rotation and angular momentum. The combination of stellar wind, mass loss, and expansion slows rotation over millions of years. Equatorial regions experience the most noticeable change, gradually reducing the differential rotation across latitudes. Magnetic field generation adjusts accordingly, influencing the structure and frequency of star spots, flares, and prominences. Observing over time, the star's activity patterns reveal the slow, steady influence of these fundamental changes. The star's ultimate fate is determined by its mass and composition. Depending on these factors, it may continue fusion in shells around an inert core, expanding as a red giant. Surface layers may become more diffuse, extending outward while cooling, while the core prepares for subsequent fusion stages or contraction. Observing the star during this phase would show significant expansion, altered brightness distribution, and evolving patterns of activity. The transition is gradual on human timescales, yet dramatic when considered over millions of years. Energy output continues, albeit with shifting distribution. Visible light may be complemented by stronger infrared emission as the surface cools. Ultraviolet output may decrease in regions where surface temperature declines. Stellar wind and mass loss remain important, redistributing matter and energy into the surrounding space. Observing from orbit, you perceive the changes as a combination of expanding surface, adjusted rotation, and altered emission, reflecting the long-term evolution of the star. Even at the final stages, rotation, magnetic activity, and surface structure continue to interact. Loops rise, prominences move, and spots appear and fade. These processes are all shaped by changes in core fusion, surface expansion, and angular momentum loss. From the orbiting perspective, you can see a dynamic, evolving star that has maintained its fundamental structure while undergoing profound transformation over its lifespan. Eventually, depending on mass, the star may shed outer layers, leaving behind a dense core. This final stage marks the end of fusion and a transition to a long-lived remnant. From a distant orbit, you would notice the surface gradually thinning, radiation output changing, and surrounding plasma dispersing. The star's influence extends outward, carrying both energy and matter into the broader galaxy. Observing these final changes provides perspective on the immense timescales involved and the natural progression from core fusion to stellar remnant. Throughout this process, the star remains a source of light, so energy and structure. Even as its appearance evolves and activity shifts, the underlying processes continue to define its behavior. Observing its lifespan from orbit, you perceive continuity and change, recognizing both the familiar surface features and the long-term dynamics shaping the star's evolution. The interaction between internal fusion, surface convection, magnetic activity, radiation, and surrounding space forms a complete picture of stellar life, seen from a carefully maintained observational path. By considering the star in terms of lifespan and evolution, you gain a sense of both scale and continuity. Each surface motion, each ejection, each gradual change in rotation or radiation is part of a long-term process that stretches across millions or billions of years. From orbit, these processes are perceptible through subtle shifts in light, motion, and surrounding material. Observing in this way emphasizes the connectedness of stellar activity, the flow of energy and matter, and the inevitable progression toward later stages of life. The orbiting perspective allows you to connect short-term phenomena with long-term evolution. Granules, star spots, flares, and prominences are seen in context, revealing patterns and trends that accumulate over vast timescales. Radiation output, stellar wind, and magnetic loops all respond to these gradual changes, creating a dynamic system that evolves coherently. The slow, steady observation gives insight into both immediate behavior and long-term transformation. Ultimately, observing the star's lifespan reinforces the sense that stars are living systems in a physical sense. Processes that seem imperceptible day to day are constantly shaping structure, energy, and motion. Over millions of years, these processes accumulate, driving expansion, surface adjustment, and eventual transition to final stages. From a careful orbit, you can perceive both the constancy and the evolution, the flow of energy, and the movement of matter that define the star's life. As the observation concludes, we begin a slow departure from the star's immediate vicinity. The pace of our movement is deliberate, giving time to notice every detail one last time. Surface features drift across our view, granules still shifting gently, star spots moving at their characteristic pace. Prominences rise and fall, arches of plasma stretching outward before settling back or dissolving into the surrounding space. Magnetic loops extend and retract, carrying energy and material along invisible lines. The star continues its rotation, a steady rhythm that marks the passage of time on its surface. From a wider perspective, the star begins to recede. Its edges become more defined against the darker backdrop of space, yet the overall brightness softens slightly as distance increases. The photosphere remains luminous, the subtle gradients of light and dark still visible, but the intensity diminishes in proportion to the expanding view. Faculae and bright patches are still observable, but from this angle they appear as small variations across the overall disk, reminding us of the scale of activity concentrated in such a massive object. The outer layers of the star, the chromosphere and corona, gradually shrink in apparent size. Coronal loops stretch outward into the vastness of space, yet from a slowly increasing distance, they appear more delicate, their movement subtle against the darkness beyond. Coronal mass ejections, previously seen rising and expanding, now blend into the surrounding space as they move outward, their structures still perceptible but less immediate. The flow of stellar wind continues, carrying plasma outward, but the motion feels more distant and diffuse. Rotational motion remains visible, though less pronounced. Equatorial regions continue to rotate faster than the poles, yet the difference is subtler from this distance. Star spots move slowly along the surface, prominences rise and fall, and magnetic loops trace their paths. Observing the star's rotation from afar gives a sense of continuity, a reminder that activity continues even as we leave the immediate environment. The patterns are still measurable, yet the overall effect is one of diminishing intensity, of the star's presence becoming more conceptual than immediate. Planets, debris, and surrounding material move with the star. From a receding perspective, their motion is less obvious but still present. Orbital paths remain coherent, debris belts maintain structure, and small objects trace predictable paths around the star. The relative motion of these bodies against the background of space emphasizes the scale of the system. Even as the star fades in apparent size, the connected network of motion persists, reflecting the gravitational and magnetic influence of the central body. Radiation continues to stream outward. The combination of visible, ultraviolet, and infrared light fills space, spreading gradually across the surrounding environment. From this increasing distance, brightness gradients soften, yet subtle cues reveal the structure of the photosphere and outer layers. Light reflects faintly off particles in the stellar wind, illuminating previously invisible components of the surrounding space. Observing the star's radiation from afar allows perception of its energy output without overwhelming the senses. The star's color remains rich, but muted as we recede. Bright yellow-white areas contrast slightly with deeper tones, providing visual cues of temperature differences across the photosphere. Faculae add minor variations in intensity, while limb darkening at the edges of the disk becomes more noticeable, framing the star against the background of galactic space. From this perspective, the star appears simultaneously unified and complex, a massive source of energy with layered structure visible in subtle shifts of light and color. Magnetic activity remains perceptible at a distance. Prominences and loops extend outward, though they appear smaller and slower. Coronal mass ejections, once dramatic, now seem like faint arcs traveling steadily into space. The flow of charged particles continues, following magnetic field lines that stretch far from the star's surface. Observing from afar highlights the reach of these fields and the continuity of energy movement, even as their immediacy fades with distance. The rotation of the star is still detectable. Equatorial drift remains faster than polar motion, granules maintain their scale, and star spots move along predictable paths. From this vantage, rotation is a slow, rhythmic process, a subtle indicator of underlying dynamics. Observing this motion at a distance emphasizes the relationship between surface features, magnetic loops, and outward energy flow, reinforcing the connected nature of the star's activity. As distance continues to increase, the scale of the star begins to recede meaningfully. Surface details blend together into a more uniform appearance. Bright and dark areas are still distinguishable, but the disk appears smoother. The contrast between prominences, loops, and the surrounding space softens. Coronal structures, though present, become less distinct. The immediate intensity of light diminishes, leaving a gentle glow against the darkness of space. Planets and debris remain part of the system, though their individual motion becomes less obvious. They appear as small points moving slowly along defined paths around the star. Asteroids, dust clouds, and rings maintain coherent structure, but from this distance, they merge visually into subtle patterns of movement. Observing. The star's surroundings at this scale gives a sense of the full system's structure, the coordinated motion of multiple bodies influenced by a single massive center. The star's energy output continues steadily. Light and radiation spread outward, filling surrounding space with energy that decreases in intensity with distance. Gradually, brightness diminishes enough to allow perception of background stars and distant galactic structures. The relative scale of the star is now smaller, yet its presence is still evident through the faint glow and residual magnetic influence. Observing from this vantage emphasizes the persistence of energy and motion across space. Magnetic loops and prominences extend into the outer environment, but appear less prominent. Coronal mass ejections move outward and begin to disperse, blending with the general flow of the stellar wind. The outward motion of plasma continues, yet the structures become subtler, merging with the surrounding medium. The observer notices the gradual reduction in immediacy, allowing for a calmer, reflective view of the star's influence at a distance. As the observer continues to leave, the star's rotation, light variations, and surface details are increasingly subtle. The disk becomes more uniform, granulation less apparent, and prominences appear only as small arcs against the outer glow. Limb darkening remains visible, providing subtle depth cues. Radiation spreads across space, energy continuing to propagate, yet the sensory impact diminishes with distance. The star's activity persists, though the observational experience shifts toward perception of scale and presence rather than immediate detail. The surrounding space shows ongoing effects of the star's influence. Plasma streams, stellar wind, and residual ejected material remain in motion. These flows carry information about the star's past activity, even as the star itself recedes. From this perspective, the interplay of matter and energy becomes more apparent. Patterns in plasma motion, subtle light scattering, and magnetic influence persist, reminding the observer of the star's extended reach. The star's disk continues to fade gradually, yet a soft glow remains. Bright patches, dark spots, and limb variations are still visible in outline, providing a final view of structural complexity. Light intensity decreases uniformly, yet gradients are observable. The star appears smaller, yet its presence in the surrounding space is undeniable. From this position, one can reflect on the scale, energy, and dynamic processes that have been observed. Observing the system as a whole, the motion of planets, debris, and ejected plasma is still apparent. Orbital paths remain coherent, while stellar wind and magnetic structures continue outward. The star's influence persists across vast distances, a continuing flow of energy and matter. The perspective highlights the coherence of the system, where individual components interact while maintaining overall stability. As distance increases further, brightness fades to a gentle, even glow. Surface details are largely indistinct, though limb darkening and subtle variations in color remain. Coronal features appear as faint extensions of light, prominences and loops blending into the surrounding space. The star remains luminous, yet the sensory impact is calm, encouraging a reflective, tranquil state. The observer is now far enough that the star's rotation and activity are perceptible only as gentle patterns in the fading light. Granulation and star spot motion merge into a smooth, slow-changing surface. Prominences and magnetic loops remain visible in outline, but motion appears deliberate and unhurried. Ejected plasma flows outward steadily, its structure discernible but subtle. The overall effect is one of calm observation, the star's presence still strong, but softened by distance. Residual glow fills the surrounding space, reminder of energy and activity that continues beyond the immediate surface. Plasma streams maintain gentle motion, coronal structures persist faintly, and stellar wind continues outward. The star's influence extends into space, leaving traces of motion and light that can be observed even at a distance. Observing these subtle features provides a sense of continuity, the persistence of energy and activity in a vast system. Finally, the star recedes to a point where it is a single luminous object against the backdrop of space. Surface details are no longer visible, rotation is imperceptible, and magnetic structures are faint traces. The surrounding environment maintains motion, but the observer perceives primarily the overall glow. The experience shifts from detailed observation to reflection, allowing a calm awareness of the star's scale, energy, and enduring presence. In this final stage, the narrator's voice gently recedes. Attention moves from the immediate surface to the star as a whole, its influence across space, and the patterns of motion that continue even as we leave. Light softens, energy continues outward, and the system remains dynamic yet distant. Observation becomes a process of calm reflection, understanding the star's size, rotation, activity, and reach in a broader context. As we drift further, the star becomes a point of light in a larger galaxy, part of a vast system of stars, gas, and dust. Its brightness diminishes gently, yet its energy and influence persist, reaching outward through plasma, magnetic fields, and radiation. From this perspective, one can appreciate both the immediacy of earlier observation and the long-term continuity of the star's presence. The motion, light, and structure are still there, but now experienced as soft, distant patterns. The final observation is a moment of reflection. The star's rotation, surface patterns, prominences, radiation, and surrounding motion have been observed in detail. Now, these elements fade gradually into background perception. Light continues to travel, plasma moves outward, and the star's influence remains, yet the immediate intensity is gone. The viewer is left with a calm awareness of scale, energy, and enduring structure. The journey concludes with the star as a soft, luminous point, the details of its surface and activity receding into memory. The surrounding system continues in motion, the effects of rotation, magnetic fields, and ejected material extending outward. Observation ends gently, leaving the viewer with a sense of completeness, calm, and reflection on the star's size, energy, and dynamic presence in the galaxy. The experience fades smoothly, leaving the mind at ease, attentive but relaxed, ready to let go of direct observation while retaining understanding and awareness of the star's grandeur and continuity.